All right, I think we're live. Had a little trouble getting the microphone to work, so I had to use the other mic, which might be okay. It's a better mic, but it's a little more
Live.
of
A
a
little
desk
trouble
hog.
getting the microphone to work, so I had to use the other mic.
It sounds okay. All right, so we'll do with what we have and such, and so forth and whatnot. I don't know what I need to. Yeah, I have to have something here to tell what's going on. I guess I could just leave that on the screen and then I'll know what I need to move. All right, yeah, it's been interesting. I think I've made lots of advances in my understanding of a few of the details about how electricity and magnetism manifest in the atomic structure of things. So I haven't got all nailed down, but if you've watched the last two videos, there's a lot of pieces I got. And so anyway, um, they're quite pleased with that. It's a big, I see it as a big, uh, there's some sort of word I'm looking for now. It's a something point, where, yes, you just have to, yes, that's where it all changed. The deciding kind of moment. It's not exactly the phrase I'm looking for, but it's one of those kind of defining moments. That's it. Something like that. Anyway, so yes, there hasn't been much at all, nothing in terms of participation by the U types. And the view numbers are kind of poor for these lecture videos, and I can understand some of that. Um, but the just the way it's going to be, which is okay with me, I guess. So I did get a couple of comments. No, just not very useful. Um, Today I was reminded you can have light microscopes to view objects that are smaller than the wavelength of light. Well, I might as well read that because that's just not right. Anyway, so the John Gray guy did post some kind of comment on one of the videos about some sort of list and some video on number 10 on the list and then number 97 on the list. I was supposed to watch number 10 on the list. And I was like, asked the simple question, what list? And he didn't answer for 2 days. Stupid shit. So I deleted that nonsense, obviously. What's the point of this shit? Anyway, so Dick asks, kind of a bummy looking fellow. Anyway, today I was reminded that you can't use light microscopes to view objects that are smaller than the wavelength of light. It really has nothing to do with it, just kind of a coincidence that the wavelength is around the same distance that things start to do the Brownian motion to such an extent that you can't see them anymore. So the fact that those two things are related is just sort of coincidental. It has nothing to do with the wavelength of the light. But if light is just the photons coming at a specific frequency, then why would it matter in relation to the size of the object? Well, it sort of would in terms of if you think about the polarization aspect of it. That's the problem, really. So the tighter the frequency, the less this you get. Okay, so the closer they are to each other, the less possibility that it can be a big distance off in terms of having any polarization. So you can think about like photons for radio or a mile apart, maybe. So big range of polarization. And then as you get higher and higher frequencies, the range of polarization goes down, 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 down until you get really tight. And that's really the cause of the fact that the photons break down as a detecting device based on their wavelength. It's because of the relationship between wavelength and how much they can be out of alignment. There's a correlation between amount of polarization and frequency, which makes sense because the photons are being produced when it comes to something like light by the same electron, where with radio waves, it's not the frequency has nothing to do with one electron producing both photons, both pieces of the light, the rays. So light is rays from atoms, but it's not really rays of radio waves. It's just a big giant pile of photons of energy, of force bits, and then another big pile, and then another big pile at a set frequency. So their polarization is almost irrelevant. All right. It amazes me that this Wheeler guy even has time to go down these Alice in Wonderland rabbit holes of his own making. Well, again, it's not even Alice in Wonderland. It's obviously that guy in Silly Putty, you know, some other quasi story, but it is a quasi story. All right, so I love this comment and the icon. Mr. Keebler says, I concede. So he wasn't on my list, as I didn't think he was a dissident to start, but maybe he did have a lack of confidence that I was on the right road in the beginning, and now concedes. Yeah, good. Thanks for that. I appreciate it. All right, so now the John Gray guy, just gratuitous crap. I mean, he really doesn't have anything to say. He doesn't have a counter argument to anything. He doesn't provide evidence of anything. He doesn't demonstrate anything. The basic accusation is that your conventional physics doesn't explain anything. Doesn't explain why anything happens at all. They just give you these, hey, this is the effects we've seen, and we got a formula for effects. We have absolutely no idea why it happens, though. They're just, yeah, this is the rule. It happens. Yeah, Ben Space, fairy farts, angel belches, and we don't care. You can believe anything you want because we just don't do cause. Anyway, don't think this is a middle school lecture, electrical engineering. I don't think they even do middle school lectures in the first place, and certainly on electrical engineering specifically. So I don't know how I possibly could make that mistake. And clearly I know their lectures. I've watched them. I've pointed out how this is MIT. You would think MIT could get the answers to some of these questions rather than just pretending they have answers. But anyway, just crap comment. This is university, like that's supposed to mean something in the context of physics that every day just makes crap up for which they have no evidence. They have no theory even defending the tools they're using. Again, why don't you tell me how the interferometer works? Why don't you draw me a picture and show me where the photons turn into wavicons and then interfere with each other and then turn back into photons? Why don't you show me in a diagram where that happens in the interferometer? You should understand and master the previous lectures. Well, I've already referenced the previous lectures. I've watched a lot of them. What I haven't done is learned calculus. So I haven't taken mathematics courses because I don't need to build an airplane. I don't need to build an Empire State Building. I'm not building something. I don't need to know the math for the effects. I am talking about modeling the causes, and that's clearly what I'm doing. And causes isn't math. Guess what? That's not how you're going to figure it out. Doing math. Doing math will not figure out causes. You have to use your imagination to try to figure out what kind of mechanism can meet the effects. All right, without the book, this is difficult enough. Oh my God. I mean, this is just so stupid. So I said, fuck you, obviously. This is a useless comment. You either defend their theory with some reference to how, well, here's proof of what he's saying is true, or you point out how I'm absolutely wrong and provide some sort of truth that demonstrates that it can't be what I say it is. But let's acknowledge this channel is called Draft Physics, Science. That is, it's a work in progress. It's one man for now like 7 years, unfortunately, but one man for 7 years proposing a theory competing with something they've contrived 1 million of them for 100 years. So they've had 100 years to work out the bugs in their bullshit. And, I'm one person for 7 years. And mine is a theory that not only unifies, it does, but it provides details of explanations of things they have never even contemplated being capable of detailing or explaining, like why magnets attract and why magnets repel. So, I mean, fuck you for being this kind of a weasel. You can't make an argument, then just shut up or go the fuck away. I mean, really. If you can't in some way rationally demonstrate how I'm wrong with something specific to what I'm arguing, not something specific to how my hair is funny. This is actually a little funny today. Cut the bangs. It's the only thing I ever cut. It's just once in a while I do that. And I didn't do a very good job, but whatever. Like you could fuck that up. But I did. So I think I'll just delete this. So I'll delete it. I won't block you. We'll see if you can grow up and make an actual physics argument somewhere. Douche. All right, that's it for comments. So I thought maybe I'll just draw with the shit I've been thinking about. And we'll see how the commenters go. I can't really play with you as easily as usual. Oh, speaking of foreign language here is really quite silly. So unless you can do English, two of you playing some sort of talk fucking bullshit game? All right, well, I can block you both. How's that? How would you like me to block you both? Yeah, it's not really a turning point because I'm still going the right way. I'm just going the right way at an accelerated rate. So it's more something other than a turning point. It's a point of maximum, something or other. So I don't know. I don't know what to do with these foreign people. I'll just delete it. That's what I'll do. That's a simple thing to do. I just delete it. Yeah, that's what I'll do. Just quit trying to find the word. It really isn't that important. So just inflection, not even close. Yeah. Inflection. I mean, inflection is it's like a pantomime or something. What does that have to do with anything? But flex is a good thing because that's like the in the physics thing they talk about the what do they call it? Magnetic flux. Yeah, that's a and all that really means is how much flow there is for this thing, whatever magnetism or electricity, how much flow. There's never any flow, so it's just a kind of a bogus concept. There's no flow until you allow there to be one, quote unquote. All right, so I guess that's the stuff I will get to drawing. So maybe I'll make this one of these on top windows so I can see if somebody does say anything reasonable. And pop this back up so I can see it. Maybe we'll just draw. I could play some, I've been watching some of the Yale ones that the whatever his name is, Sinkar guy. And like I said, I like him, but he is dry and it's just all equations. There's no demonstrations of anything, no nothing. But I was also noticing that the demonstrations are always kind of problematic because of the way they engineer them. And they're not really, they can mislead you. And so I've sort of found that fault in the past with Professor Lewin's demonstration of the radar experiment, where I say it's clear that it's jamming. The two signals are jammed. There is no interference. There's no radar plus radar equals no radar. The radar is there, just that the signal can't be interpreted by a normal receiver because the two signals are on top of each other and it can't tell which signal, because they're out of phase, it can't tell which signal it's supposed to be receiving. It's not receiving the signal at the right frequency, so it can't be tuned. Anyway, so Gary, here we go. Yeah, I mean, this is so irrelevant. is the universe deterministic? That has nothing to do with anything I've added to theory. So it was deterministic even by the dopey theories. I mean, except for their idiotic crap where they make up this crap that there's some, like Feynman's interpretation or something, where there's some sort of random thing that happens. Like the photons are just randomly leaving the two-slit experiment in any direction. Like, obviously, that's just silly. And obviously, entanglement is silly. So it was deterministic before they invented those two idiotic notions anyway. But yes, clearly it's a mechanical system. If you think it's doing something other than actually mechanical things are happening, I don't know what you think would make it undeterministic. Magic fairies, right? I mean, how would the dumb universe get undeterministic? I mean, really, how could it do that? We have absolutely no evidence of it. Moons just don't disappear. Things just don't randomly happen. And so the one place you say it's undetermined is where the little teeny tiny things are that we can't see. But obviously it's deterministic. Yes, the answer is it's determinate. Of course it is. It's a mechanical thing. Doesn't have any angels in it to do something undeterministic. And even the angels would be deterministic in a sense, right? Because they would have a life experience as angels. And their life experience as angels would decide how they behave, right? And they would still be stuck with knowing 2 + 2 = 4. So I'm stuck with 2 + 2 = 4. I can't pretend it equals 3. So yes, I'm stuck with this. So they're going to be just as deterministic as the rest of us robots. So even with angels, you're still fucked. All right, anyway. When a force bit leaves perpendicular from matter, is there a way to determine which one exactly? Which dimension, I guess he means. You can go this way, this way, this way, or this way. So it has those 4 choices. Can't go this way, can't go this way. It has to go one of these. And yes, the what would determine it is the previous state. So that sort of indicates why the 2-slit is deterministic. It's because the previous state does affect the next state. So if it has more energy going one way, then it's more likely to leave in the direction it has more in. So that's, by the laws of probability. So it's the same reason it would lose acceleration in a direction. It's the same reason it will preference certain directions. So if it's vibrating like this, then when it's going this way, it'll go right. And when it's going this way, it'll go left. That kind of thing. There will be a right-hand rule, so to speak. All right. Is there a way to determine which one exactly? Well, exact, I don't have that part of the model yet, so I can't give you an exact, because I can't give you an exact reason why it's perpendicular, beyond the fact that that's what it does. But yes, if that is ever deduced, then you can have a more specific answer to why, you'll have a better understanding of why there's a difference between hitting the arrow on this side and hitting the arrow on that side, or whatever the reason is. Which of the possible perpendicular directions? Yes, that's what I just explained. Okay, good enough then. Seems satisfied with the answer, so good. All right. Yeah. So the interesting subject is this whole how the field migrates, and how it affects a piece of matter that gets into the field, and the difference between the monopoles and then creating dipoles. That is, having charge and then having 2 charges of opposite character when they actually are put next to each other. What does that mean? What does that create, and how that changes things? So the part that is going to be the next part of the Professor Lewin video, because I have played the second half that I haven't done yet. And he sticks the fluorescent light into the field. And there's so much going on there that's subtle. And what he does is he puts his finger on the end of it and makes the light brighter. Now, that one's kind of obvious, right? I mean, he's creating a pathway for the pressure. So, of course, it would get brighter because now it has a pathway it didn't have before. So now this stuff can move. But it also gets into this whole subject of alternating current versus DC current, and why when you stick a magnet into a field, you stick it in, it has an effect while the magnet's moving, but as soon as you stop the magnet and stop moving anything, there's no simple word for that. Well, what's the simple word of it when you impose I mean, you're just using it every day. I don't know how I can forget the word. Oh, I use it when I talk about gravity. It's inductive. Okay, so all of a sudden the induction ceases when you stop moving. Everything ceases. Everything just stops. And it's only when things are moving that the magnetic field is created. So it's as if the polarization disappears when there isn't something moving. And so there's a reason for that. So we'll go through some of that stuff. But it does get kind of complicated with the fluorescent bulb in a strong electric field, because the atmosphere confuses the subject a little, because there's every possibility that the atoms in the air are getting charged just like the bulb, and that those charged atoms will hit the electrodes, and that on both ends, and create a pathway for the current. So it might not be the field that's creating the light, but the fact that the field has electrified the atoms in the atmosphere and allowed them to move through the light. And so I just don't have any knowledge. I don't know for a fact that if in space I have a Venn diagram and I create 300,000 volts, and then I put a fluorescent bulb next to it, will that bulb light up without the atmosphere to help? So is the atmosphere helping to light the bulb, the atoms in the atmosphere, or is it purely an effect of the field pressure? And I would argue, I think I'm going to argue, that it wouldn't work in space. It wouldn't work in a vacuum. So if you stuck a fluorescent bulb, if you put a Venn diagram in a vacuum, got 300 volts on its surface, stuck a fluorescent bulb in there, it won't light up, even if you touch it, unless you have this end really, really close. I don't know, impossibly close, where you start ripping atoms off of the Venn diagram to jump to you create a plasma that'll jump, a St. Elmo's fire or whatever. I don't know why people do this stuff where they write stuff that just doesn't have any meaning. I just don't get it. Kirkland greater than Kroger. Just don't understand what that could mean to me. Ed. No, I don't. And possibly bizarre. So I'll delete it I wish they just had a delete button instead of having to open this whole fucking idiotic window. They ought to just put all the little icons right there so I can just hit one of them, be done with it. So anyway, if anybody does have any knowledge of whether you can light a fluorescent bulb in a vacuum with a voltage, I'd be interested. And I'll just go for my description with my conclusion that it really can't, because there's no way to move the pressure. The pressure has to be released somewhere, and it has to be released through a conductor. So without a conductor, you're not going to get anything but a tiny little flash when you first push the bulb in. Maybe if you push it in fast, you get a little flash of light, and that'll be the end of it. Because the pressure has to go somewhere. It's just the way it works. And it's not an alternating current coming from the Venn diagram. It's not herky-jerky. so it can't use the herky-jerkiness to move, to create artificial movement in the bulb. I mean, the same, you could sort of understand that having an alternating current would be very much the same thing as me moving the bulb back and forth, right? So that could create a bulb that stays lit. If I move it back and forth really quickly, then I could keep it lit in a DC field. All right, do all times. Oh man, you people just can't stay on any kind of rational subject. I just can't imagine how you can waste your time thinking any of this fucking time crap means anything. This stupid frame bullshit. You're just so caught up in this nonsense of stuff that we could never know anyway. Even if it was true, you can't access. You can't even do experiments to access any of this shit. Do all times exist at once? No, it's complete nonsense. It's a mathematical gimmick. Feynman admitted it was a mathematical fun. It was a toy. This idea of, well, I can make the electron go back in time and call it an antiparticle. I mean, yeah, you could do that, and then Dirac's equation makes sense. Well, Dirac was insane, frankly. I mean, if Dirac's equation makes sense by you taking electrons and moving them backwards in time, then there's probably something wrong with his equations. You know, this is so dark and mattery. Like, oh, we fixed our math with something absolutely preposterous. Let's invent some kind of weird matter that's just like the invisible man of matter. I mean, it's not they said the wildebeest of matter, like it was somehow related to being at least a life form or something. No, they went clearly for invisible man. Might as well be invisible platypus. But I mean, it's just, it's such a reach. Oh yeah, it just happens that there's invisible matter in the universe that fixes our math. And that's all this B theory crap is. It's just bad. They're fixing errors in their math with completely made up, let's just make stuff move backwards. Or let's create 11 extra dimensions so we can get rid of all our errors and just sweep them under the rug in the multiverse. You know, we can get rid of all our problems by just sweeping them into another dimension. It's just so bad. Well, look, you're on the wrong channel, so I don't know what you want from me. I don't do this, okay? Relativity is a pile of horse shit. There's no such thing as a time dimension. There's no space, time. There's space and time. They're two separate things. Space is a real thing with 3 dimensions and presumably nothing in it until you put something in it. Okay, but space is a geometric location in 3 dimensions. Time is merely the byproduct of things moving slower than instantaneous. If everything moved at instantaneous speed, then there wouldn't be any time and there wouldn't be anything. But but there's no time dimension. It's an idiotic notion. It's bullshit. It's nonsense. It's a frickin' walking card. It's a disappearing cat. It's a talking caterpillar. It's a rabbit with a clock. It's just crap. So I'm not doing that. I'm doing fundamental physics, not drunken imagination physics. Okay. Pretty much. So a little more nicotine before I start drawing, I think. Yes. Need to eat more. It takes work thinking. So they just keep doing all this crap. Was the initial state of the universe necessary or contingent? I just couldn't care less about this again. I mean, you want to worry about it. I'm saying the initial state of the universe was dumb, okay? And it never got any smarter. So it's a dumb bunch of crude mechanisms. There's no initial state. We need a proofter. We need a magical thing. No, it just gets more and more elemental till you get to something just basic, and that's what the universe does. That's its basic function. Okay, so there's some point where clearly it makes something. So it's a something engine. Somewhere there's a something engine. And that's what it does just by its function. But there isn't something that makes the something. Because obviously that would be more complicated than the something. Then you'd have to say, where did the something that makes something come from? So all of these questions go absolutely nowhere. The answer will not be profound. It just won't. Because if you find your talking frog god or whatever you're looking for, you're still going to be stuck with a question. Who the fuck made that thing? What universe did it evolve in? I mean, you're just going to end up nowhere. The answer is just going to be it's a stupid fucking mechanism. And already I'm arguing that we know it's pretty elemental. It's pretty checkerboard, even by my theory. And it might get even more checkerboard. I mean, even more, it's just things in a position. It's just patterns moving through space. I mean, it can get even more vaporous and simpler. There's just locations in space that say on, off, on, off, on, off. Get it? Black, white, black, white, black, white. That's essentially the universe can be that simple. That's all there is. Just cards that flip black, white, black, white, black, white. That's it. There's every reason to believe that's how simple it goes. Do you need an explanation for that? Yeah, well, the present doesn't really exist. The present is like a spark between the past and the future. The present doesn't have any, oh, I'm in the present. No, I already missed it. I'm the present. Oh, damn, missed it again. Yeah, present doesn't even have a position in space. It's so small. The universe is ones and zeros. Well, I just said black and white, but whatever. If you want to use your little ones and your little zeros, okay. I don't care. This could be a picture of a frog on one side and a dog on the other side. It's dogs and frogs. But whatever. Are you familiar with the Game of Life thing? I don't know. There was a game called The Game of Life, board game. I've seen simulations of life, but I don't know what the Game of Life thing is. I guess I'm not familiar with that ambiguous quotation. So, yes, it's an ambiguous quotation. Now, I don't think I know what that is. But it's clearly not going to have, I bet you it's not going to have too much to do with what the subject's supposed to be, which is how does the electric field cause effects, spooky action at a distance? How's it do that? Yeah, I'm providing an explanation for that, where they don't provide any explanation. It's just funny. You people don't seem at all. They provide you no explanation for why two magnets smash together and fly apart and all that kind of stuff. And you're sitting here worrying about, what happened 17 billion years ago. I mean, just bizarre. There's the superior mind coming to the rescue. Yeah, it's all about the pressure. Pressure. The whole universe is made of pressure. It's so obvious. The little atoms are under pressure. The atoms together are under pressure. We are under pressure. The earth is under pressure. The moon and the earth are under pressure. The sun, the moon, the earth are under pressure. The solar system's under pressure. It's all pressure. Durr. Look, I obviously I don't care. Whatever this Conway's Game of Life, who cares? No, I'm not familiar. What could it possibly have to do with physics? Your stupid Game of Life crap. It's the other look. Are your force bits just photons? No, it's the other way around. Photons are just the force bits. Jeez. Just I have to go over this over and over and over. You should be up there. You should be up to speed on this fossology guy. Damn. Photons are just force bits at a distance. And they're electron force bits. All right. So I guess I'll get on with my drawing. And periodically pay attention to you flat-headed fucktards. Sorry. Unnecessary reference. Okay, so what we're trying to figure out is we have the Venn diagram. Yeah. So we'll say it's positively charged at 300,000 volts. A lot of voltage. All right, so what it's doing is, by theory, is it's creating a substantial amount of extra. So when it's this positive voltage, it makes it a little bit confusing, but we'll just leave it that way. It's producing more of this red stuff, okay, than brown. Now, in theory, it's probably a tiny percentage more, but we'll, for the sake of making it illustratable, we'll make it 25% less, 25, 75, or whatever I just drew there in terms of proportion. So there's the force coming off the Venn diagram. The little bits are much more red, much more often red than black or brown. So you can see that. Okay. So they're coming off as rays, and that can be thought of as at a distance. This distance between the rays is essentially dictates. You can sort of understand that at a distance, if I extend those lines, I got to keep everything in the frame, damn it. All right, well, I just do this for the sake of illustration right now. You can see as distance increases, the separation increases. And that means it gets weaker and weaker as this separation increases between the lines. So you can sort of understand as it goes distance, it decreases. But this one only decreases at the R rate, okay, just a R rate, which means as you double the distance, you have the field, the strength. So at this distance from the center would be the R. It has 300,000 volts on this surface. So if I double that distance, I'm down to 150,000. And then I make another, that amount of distance change. I'm halving it, so I'm down to 75. All right. So the idea is there's little red bits and little black bits flying through the air. So gravity comes into this thing, all right, as mixed, totally randomly mixed, and it's coming out of this thing, not random, okay, more red than black. All right, and so it's raining that on everything out here, and it's raining it based on this slight decrease in its strength over time. So look, superior mind, don't even bother with this meta character. Look, go away, meta character. No one here wants to play with your God stuff. So if that's what you're about, just shut up, get the fuck out of here. If you're a religious kook, you're wasting your time, and you're wasting the time of anybody who's rational commenting. This isn't a place for kooks. Religion is silly. It has no grounding. It's as bad as believing in the Easter rabbit, or Santa Claus, or Puss in Boots, or fairy godmothers. It's retarded. You're just saying I'm a screaming asshole, okay, who has to contrive a reality because I can't live in the real world. You're just a fucking truth denier. The evidence is overwhelming. We evolved on this planet, and there's no evidence of any intervention by any kind of fucking superior or even inferior superpower. Just grow up and get into the real conversation about things we can understand, which are the mechanics of this universe. You dumb fuck. Quit wasting your neurology looking for fucking invisible men and free lunches. Anyway, so the scenario is we're going to place a fluorescent light bulb. Let's see if I can do that with some other color, not to mess up everything with colors here. So we're going to put a bulb in this field, and it's going to be affected. And the effect is going to be that this bulb will light up a little bit. And if I put my finger from ground essentially and touch it, it'll light up a little bit more. Not huge, but a little bit more. Obviously, if I turn the bulb sideways, it won't light up because the force will be equal all the way across it. So there won't be any voltage difference. So what we're really taking advantage of is the fact that, let's say this is, say, 50,000 volts here. We're taking advantage of the fact that there's a 100,000 voltage difference. Okay, so the difference in the voltage from one end to the other end, based on the grade of the field, is 100,000 volts. And so that's the scenario. Now the question is, what's happening inside that bulb? So what I'm arguing is that maybe I'll use another piece of paper so I don't make too big a mess here. Maybe I can reuse this one. Yeah, I can reuse the paper. All right, so we know there's, like I said, we know there's atoms in the atmosphere. So I don't want to get into that crap. All right, but so let's just say there's atoms inside the bulb gas. There's atoms in the electrodes. There's atoms in a lot of places, but let's just deal with the bulb for now. All right, so what's inside the bulb and what's going to happen to the stuff inside the bulb? And it's connected with these little electrodes, but just for the simplicity, let's just deal with the bulb and the atoms inside of it. So what's going to happen is the atoms are basically just a proton, a little red bit, and then this electron crap going around the outside. And so now we're hitting it with a more red than brown, which means that the reds are going to get bounced back. They're going to reflect off the nucleus, but the nucleus is very small. I mean, it's in size. So it's hard to hit the nucleus, easy to hit the electrons. So the average atom, so let's just deal with the electron effect, because the proton effect really isn't all that interesting. But the electron effect always is, because they're out. They're not a tiny speck. So they're affected by things more. All right, so anyway, so we know that the gravity on both sides of this thing are coming in this way, with this mixed force. And that what's going to happen is now this force is going to come in that's going to be red dominant. So it's not going to have any of that brown energy in it that's going to bounce off the electrons and push them this way. So they're going to get more brown hits this way than they'll get this hit this way. And that's going to mean more an incentive to go, let's draw it the right way. So more brown hits from the gravity side, because it still has 50-50. So it's still 50-50 here. And it's only, so there's less brown. You can see it. The drawing sort of illustrates it. Let me put more brown in here. You get it. All right. So there's more push this way to the electrons than there is push from the changed gravity coming from the Venn diagram. So the Venn diagram has changed the gravity that was coming in this side from the Venn diagram, right? It converted that 50-50 into whatever it is now. We'll just call it 70-25 or whatever. So it converted 50-50 into something that's mostly the red force. And now it's only 25% of that brown force. So now the gravity on one side is stronger, essentially, in terms of brown force. So anyway, the bottom line is you can sort of understand the atom electrons are going to tend to go this way. And so as they do that, they're next to each other. So the other thing to understand, so when the atoms are, in a substance, they're close to each other and, jiggling and such. And so as they do this moving thing, they're pushing on each other. And so the process of all of them wanting to go this way. See, this one wants to go there the most because it's the one right by the side. But the rest of these are the guys that are really are causing the pressure. Even though theirs is less pressure, they're going to cause the pressure that's really going to compress this one. So it's the same thing. I've used the analogy of gravity and underwater. The gravity makes the water heavy, okay? So even though the gravity is getting weaker as you go down, the real gravity, the deeper I go underground, the less gravity there is. The trick is, right, is that the pressure gets bigger because you have all this layers of stuff that are going to be pushing. So even though they're being pushed by less gravity, it's only 5 meters per second and 2 meters per second or something. It all adds up because it's all on top of the guy sitting at the bottom. So he's getting crushed by it. So this atom will get crushed a lot more just by all this weaker stuff all the way to this 0 point. And so what's basically going to happen is these atoms are going to start pressurizing, that is compressing. So they're going to get smaller. You could argue that the orbit of the electrons will compress, and that's where the little bits inside now are moving faster because they're getting pushed closer together. And so it gets the electrons get smaller. Now, as the electrons get smaller in terms of their circumference, that means they're blocking more of the proton, right? So as the electrons move in, that means they're in front of the proton a lot more. So they're blocking the proton energy. So now they're becoming charged. They're becoming themselves not neutral. They're not, they're not at the perfect distance where, well, I've sort of explained this in other videos, but you can sort of understand the proton is this kind of amount of charge and the electron is this amount of charge. Obviously, if I move those, just right, I can get those two things to be the same size. That's ground. So this is the ground state for atoms, where the proton equals the electron at this distance. I go further forward, the proton gets bigger relative to, the electron gets bigger, and I go in, the proton gets bigger. But the point is that's where this analogy breaks down, because the point is the electron blocks more of the proton. So if I used a light bulb, you could understand that if I have a little ball and I move it further away from the light bulb, you'll get more light from the light bulb. And the closer I move the little metal ball, the less light you'll get from the light bulb. That's a better analogy. So anyway, so as it compresses, the atoms are now becoming ions. They're becoming charged, okay, just because of the compression, the pressure. And the other point is in a conductor, we know that they exchange this pressure readily. So let's say there's little electrons in between each one of the atoms. So there's some extra electrons, and those electrons, when it goes from, I have to draw a bigger picture so you can see it. So if you have two atoms and one of them's more pressurized than the other, and there's an electron bouncing around in here, and it bounces into this one and into this one, he'll convey the pressure. So if the electron moves into this high pressure one, the electron will pick up that extra pressure and hit this atom harder. And that means it'll compress it and pressurize it. And so then the pressures will come, they'll equalize in the sense that this one will lose pressure. So it'll gain a little bit, it'll get a little bigger from the impact. This one will get a little smaller from the impact. And so they'll start to average out. So in conductors, whenever atoms get whenever they get pressurized, they spread their pressure. So what's going to happen from this fluorescent bulb from this Venn diagram producing all this energy, this 300,000 volts that we've decided is 100,000 volts remaining across this distance of the bulb, is that yes, all the electrons are going to pressurize. They're all moving towards one end a little bit. And it only takes a little bit. There's very little space inside of here, as much as they say, between the electrons and the atoms. The atoms are close together and it doesn't take much inclusion. So when they say this is an electron from one atom and this is the electron from the other atom, they really don't like each other very much. And so there's a real tension between them. But there's a real attraction from this electron to the proton of this atom. So, they're in a really, tension. They're in tension. And so it doesn't take much movement to create pressure. The pressure that changes from positive to negative isn't much of a pressure difference. You don't have to make them, I'm drawing them huge differences, but the difference, just tiny, is all you need to polarize, to create a monopole of charge. All right, so what's going to happen to all these atoms is they're going to start pressurizing, and they're all going to be, because it's a conductor, they're all going to equalize at this smaller pressure. So eventually, even though they're in a pressure that's uneven, the field pressure is 100,000 volts here and only 50 here, they're actually all going to end up being the highest pressure of 100,000. So they're all going to end up going to the highest common denominator, whatever you want to call it. Yeah. And the trick is, though, see, because there's this trick. If this was just a regular conductor, or if this was just two balls I stuck in this field, two metal balls connected to each other, the real trick is if I tried to separate them, then I cause a current. Okay, and when I cause the current is when I make one low and one high. So it's only at the point of separation that the lower pressure in this end it moves, and the other one, the high pressure, moves, and they become a dipole, in that one has the high pressure trapped in it and one will end up having the low pressure. But that only happens if I attempt to divide, because as I'm dividing, the pressure exchanges stop leaping across, so they're diminished. And so one side ends up giving away all its pressure and it can't get it back. One way of saying it. All right, that needs more detail, but it'll just confuse this subject for now. So I don't want to do both subjects in this video. I don't really want to do either one. I'm just explaining how the mechanism is really simple. So all you're talking about is making atoms bigger and smaller. And when they're big, they're a positive ion, and when they're small, they're a negative ion. And that's all. That's all that's happening. And when you put a bunch of the same ones, a bunch of big atoms into one thing, then you've charged it, and it's like a balloon or something, and you can put a bunch of big atoms in it, and now that's charged. It's a plus monopole. And if you make it small, then it's a minus monopole. If you can make a bunch of small ones stuck together. And again, if they're a conducting surface or a conducting thing, they'll all end up having the same charge. And so it'll be essentially, all brown energy or all red energy in terms of what it reflects. Not only what it reflects, oh, sorry, that wasn't in the picture. Not only what it reflects, but what it what it reflects and what it produces, in the sense of energy goes in and comes out in that form. It converts gravity and separates it, essentially. Separate's the wrong word. That's not entirely wrong, but for charge, it's wrong because, yeah, they're just more red reflective. So a charge takes what the world gives it and reflects it back disproportionately. So all the black energy that hits the charge goes right through it, the positive charge, and all the red comes right back. So that's why the charge behavior is essentially dictated by what reflects off of it. So it's not filtering gravity by itself, it's reflecting it. And it's completely a phenomenon of reflection. Reflection is what's creating the filter in the sense. So maybe I'm reduced all the way to that. So anyway, the point is that once these all charge up, so I shove the bulb in, I might get a tiny pop of glow out of it in, let's say, free space. But once the bulb is in position, there shouldn't be any light. And so my argument is the only reason why there's light in this bulb is because the atmosphere has atoms in it. And the atmosphere atoms are doing the same thing. They're charging. They're getting big and small. And they are in this environment. And so these atoms are detecting those atoms. And the ones here are not pressurized because they're not connected to each other. They're, very well. So these are at a very low voltage relative to this interior voltage. And so they're going to exchange pressure readily. And when they do that, that's going to cause movement again, because now we're going to have more exchanges. So the exchanges in pressure are what's changing the polar state of the atoms. And changing the polar state is what creates the magnetic effect. So I guess a way to describe that. So I just want to get through this argument. So I'm going to argue, I'm contending that the atmospheric atoms are the ones that allow for there to be a current. So then when Professor Lewin touches this end of the bulb, what he's really doing is providing an outlet to ground. So he's putting zero charge here. And that's creating a strong exchanges are happening, high pressure to low pressure exchanges. And so all this pressure is being eaten up by that ground. And the thing that limits it being a really strong current and electrocuting Professor Lewin is the fact that there's not enough atoms in this atmosphere to move any current. So current just doesn't move. But this really isn't contingent on somebody. I mean, I have someone have to find the experiment of a fluorescent bulb in a vacuum and to see if the fluorescent bulb in a vacuum lights up if you put it in a charge field. Because I would argue I don't think it theoretically can. All right. That was something I wanted to go over. There's so much. It's really simple. It's just it's getting big, getting small. Really simple, but there's so many little nuances to it. So the polarization part kicks in is that when the current starts flowing, you can sort of understand that the atoms are going from being little atoms at one end, pressurized ones still, and they're getting bigger and bigger and bigger. I'm really exaggerating, as you're letting it out to ground. So the ground atoms are big, and you're essentially, it's conducting that ground pressure into the high pressure, but there's always a more source of high pressure. So the more high pressure keeps coming in, and you have this differential between the high and the low, that becomes a reality. And now you've polarized the stuff, and by polarizing, you essentially create a magnet, a red end and a black end. A high pressure end and a low pressure end. And individual atoms will also be becoming magnets because now there's lots of atoms that are going to be side by side, a high pressure atom side by side to a low pressure atom, because they haven't exchanged pressure yet. The pressure takes time to be exchanged. And so as long as you allow the current to flow, you'll have a magnetic field. But as soon as you stop the current, all the pressure will equalize again, and you won't have any magnetism. Okay. So I think I've explained that. I think you can either think I did or didn't. But anyway, it's just part of me doing this was just to see if I got the answer, if I'm ready to provide this answer. It's not a bad answer, so I'm going to try to provide it and see if I put it in words that are better understood. Because I really should be able to get this to you to understand that the pressure change, all right, just changing that size also is changing the polarization. So I don't even have to warp the atom to change it. I've changed it by just changing the pressure. I've changed how much the electrons are essentially blocking energy from the proton. So it's automatically making it as an entity more look like an electron. So it's like I've said before, you could almost think of it that way. From a distance, looking at it, just by changing how far the electrons are, I could change the appearance. So if the electrons actually were black and the proton was actually red, and I started compressing it, there'd be a point where from a distance, it would look red. And then as I compress it, it would turn black. And then there'd be the neutral point would be brown. So, it's that obvious a kind of a thing. You're changing the polarization by changing the pressure. So that connects the electric phenomenon to the magnetic one. Pretty clear connection, I think. All right. Let's see. These are all 3 4-letter sentences that aren't likely to be much fun. All right, let's see. Force bits are photons and more. It's not like they're more, in the sense that magnetism is just, yes, it's just style. It's styles of the same thing. It's all hair. It's just styled differently. So a magnet styles it differently. Photons are a little different style, but it's, same thing, just a tiny difference. Force with frequency. Oh, frequency. I get it. Okay. So yes, force bits add a frequency. Not complicated. Bullets add a frequency. Cannonballs add a frequency. Just isn't. It's that simple. They're just little bits being shot, okay, at a regular interval. Do you believe in God free will? Okay, we already did that. Rosie O'Kelly, is it JAP Tanny Chaser? I don't know what that could mean. I'm just going to block you. All right. It's too stupid. Whatever it was. Too stupid. All right. Magnetize. It's kind of relative to how visible the proton is with size due to tension. Well, I'm just saying for the atom, the protons are opaque and the electrons are opaque. So force doesn't go through them. So the proton force can't get through an electron, so to speak. It's bent sideways, quite obviously. It's opaque to the force, the opposite force. Let's see, reduce the neutral to make more like electron behavior. Reduce the neutral to make more like electron behavior. Well, I don't think that doesn't make any sense to me. The correlation I'm seeking is to fit all of the evidence. So the evidence is that like, for example, X-rays, you want to make X-rays, you have to put energy in to atoms. And the idea of putting energy in means compressing them. So that perfectly fits that the electrons are closer together. And that's why you can create an X-ray. It's because now there's a tight frequency. The electrons are very close together, very tight frequency. You create X-rays. Very trends are far apart. You create, infrared. So that's the correlation I'm saying. This sort of has to fit. is that there is a huge connection between the idea of pressure or energy and the idea of making ultraviolet light. Even ultraviolet light requires more energy to produce. So it's like you have to pressurize the atom to create that. You have to make those electrons closer together to create that energy profile. And so that part fits. And it also fits that the connection that when you are pressurizing these electrons, that that process is creating difference in their charge profile, which is going to make them monopoles of different charge, and therefore they're going to produce a magnetic field. Yeah, I think so. So anyway, this is, like I said, this is a, I mean, it was big when I realized the two force thing. That was a huge step in the progress of this theory, the two charges of force, the two varieties of force. And then using that to create magnetism, the obvious filter thing. And then this, I mean, you know, it just provides this a clear way to understand the difference between charge, monopoles, magnetism, dipoles, and pressure, which is the only part the atoms, that's how the atoms make the monopoles, is through their pressure. Weak pressure, positive monopole, high pressure, negative monopole. Yeah, tighter electron distribution under pressure, smaller atom, and a tiny, it's like I said, this isn't like they're getting dramatically smaller. You know, it's a tiny difference that creates the effect. Smaller atom will act more like positive charge monopole, right? And conversely for the other way. I'm just saying it. You could just think of it as color. That's the way that's what's going to happen to it. So the proton's a little thing in the middle. You got those black things on the outside. I'm just saying if you move the black things closer, you know they're going to be blocking the red thing a lot more. And the further away I move the black thing, you know, the less and less they're relevant, and the more relevant this red color becomes. There's a point where the two colors are equal in terms of their distribution, and then everything else is either positive bias or negative bias, red or black. This is equal 50-50, and you go out, you've changed the 50-50. You go in, you change the 50-50 in the opposite direction. That's how easy it is to create a positive or a negatively charged object. Yes, I just wish it wasn't quite, like I said, I wish it didn't have this nuance to it. There's a little bit of nuance in this stupid question of, you know, the fields aren't pure fields. Again, we're doing this experiment in an atmosphere, you know, and we don't have the direct comparison of doing it with no atmosphere to be sure, you know, what's really causing it. But I think the logic I've provided here is solid. I don't think I'm going to be changing too much of what I said in future. I mean, I don't think my refinements that are always, you know, there's always refinements. There's always, look, 2 weeks ago or even a week ago, I was kind of talking about the atoms being distorted in their shape or bent. And you really don't have to do any of that. You can create the dipole by just having two atoms next to each other that are of different pressure. And so they're a dipole until they finally neutralize and become the same pressure. So while they're different, they're a dipole, they're a magnet. And it isn't until they're both the same size that they become either a monopole or they become the same, the ground pressure, and become invisible, quote unquote. uncharged. And so invisible would be like you look like gravity. So in gravity, if you want to look like gravity and be invisible, then you would do what gravity does, which is you'd produce 50-50 force. If you reflect 50-50, you'll look just like gravity. So gravity's coming in 50-50. If you reflect 50-50, you'll look just like gravity. No one will know you're there, so to speak. And that's what the neutral is doing. When you're charged, you're giving yourself away because you're reflecting the wrong amount. You're creating 60-40 reflections. You can't do that and not be not noticed. You'll be noticed. So that might be a simple way to understand it. If you're doing 50-50, you're an invisible man. So if I'm doing exactly what the environment's doing, like if I project what's coming from behind me and I just project it out the front of me, I'm invisible. So if I do what the field is doing, I'm invisible. But as soon as I change what the field's doing, I do something other than what the field's doing, I'm going to be obviously unbalanced. I'm going to be either positive or negative. I'm going to be black or red. Yes, it's just so simple. So simple. Fat, thin, so simple. So anyway, I really feel, a lot of progress in the last 3 days. But I mean, I've felt optimism before, and it's been a waste to feel optimism because the audience is so cement-headed. Until I give them every single detail, they're just going to keep trying to find a reason not to accept this is such a good answer. So much better than the non-answer physics provides. They don't give you nothing. They'll give you nothing. They'll give you an equation that says, well, this is what the effect always is. And they'll give you no reason. They'll give you an idiotic reason in the sense they'll say there's two kinds of fields. There's, that's the electric field. No, yeah, that's the magnetic one over there. And that's something called flux over there. So there's flux over there, an electric field over there, and a magnetic field over there. No. One pile of stuff. And all you're doing is making subtle changes to how it's reflected. And it's really just about the reflections. It's really just, that's all it really is. You reflect more red than black, you're a positive ion. You reflect more black than red, you're a negative ion. It's that simple. Yeah, well, it all goes back to Maxwell. Maxwell created the idea of merging and creating the electromagnetic spectrum, calling it that. And so he magnetized and electrified photons, which have no business being magnetized and electrified because they have nothing to do with either a phenomenon in a sense. Obviously, they do have something to do, as I'm pointing out. The pressure will decide what flavor photon you'll get, what color it'll get. Yeah, the two fields. Like I said, this goes back to when I was a kid, this stupid explanation. The field, it's moving in the electric field, and then it's moving this way in the magnetic field. And yeah, it's just unnecessary complication. The simplest elements in the universe are not doing this and this. It's just no. And they should have known better. But it gives them a way of see what's really separate. Another part of this. Okay, that's another good. I have to write it down because I'm not going to remember. There's a correlation difference. So sometimes you have things that are correlated at ratios. Like for every one step forward, it goes 2 steps up. And so the interesting thing about spherical geometry, right, is that you make the differences you're making in terms of how much you expanded the circumference over a sphere. So the little change in the out direction, the direction you moved, creates a r squared effect kind of thing in terms of how much area you created. It's new area. So the trick is that the charge effect lags the electric effect. So the electric effect is moving this way and it's really sensitive, but the charge effect, right, is disproportionately slower. So that's why the electric effect has the longest range. The charge effect is the r squared, and then the dipole is the r cubed. So in terms of how fast the force diminishes or weakens, that's the relationship. And the relationship is based on the fact that you're going from something that is linear to something that's spherical. And so you're making a linear change in pressure, but you're making a spherical change in its in the magnetic effect. And so those distinctions are what creates the difference in how in some of the reasons. No, it's only part of the reason. There are other reasons why one's weaker. And the obvious reason for dipoles is you have two monopoles that are doing the exact opposite thing. And so the closer you bring them together, right? If you could take two charges, a +1 charge and a +2 charge, and you could actually literally smash them together, you'd have nothing, right? You have a nothing charge. So if you put them right next to each other, you're still diluting them substantially. And the further apart you put them, the stronger they are, because they're more free of this idiot undoing everything this guy's doing. So this guy's doing red and this guy's doing black. And you can sort of understand that the world is a lot redder if this black guy doesn't keep putting black in my red. So if I'm making a red canvas and my right hand and my left hand starts throwing black, you can sort of understand that the further away I put that black hand, the more red my canvas stays. So that's sort of the reason why there's a difference in how fast the force deteriorates. So obviously the dipole, it dissipates the quickest because there's a guy, you're polluting each other's painting. And then the single charges, they're pretty good paintings, okay, but they're the strength is just stuck with the spherical geometry thing. They're going to radiate in all directions, and the lines are straight line force. So the charges just represent straight line force and its implications. But the pressure argument, right, doesn't have the same spherical geometry problem because it's you can't, let's see, what's the right word for it? Right way to describe it. I'll have to think about it. Yeah. But it has to do with the fact that you're pressurizing the atoms by just sort of expanding the diameter. And that's just a linear line. So this versus the whole sphere thing. So that's what it has to do with. I just don't know how to say that. How to provide an example. Good example. So I'll save that for later. But that is something to understand. So the electric effect, the pressurizing of atoms, goes the deepest into space. The charge goes second, and the dipole magnet goes the weakest in terms of distance. But it's ironically the strongest when you have them really close, because you're basically putting the opposite monopoles as close as you can to each other. So obviously you're maximizing their impact. Yeah. I like that good enough. Now maybe I'll put up my list of little, got to write some more stuff because, but some of this is good. So we'll put that on here. I guess I could use the full page. I don't see why. Oh yeah, that's why it goes the wrong way. That's why. Yeah. Let's see if I hit the shift key, I might be able to do this. Yeah. All right, that works, I think, without making too big a mess, I think. Yeah, that looks all right. Close enough. I guess I could move it over a little bit. Whoops. Oops. Well, I guess I shouldn't move it over. I should just make it a little bit. Oh, damn. It undid what I did. Bastard. Always little tricks to this game. Every piece of software, you have to learn all these little nuances. Eesh. Yeah, I like that. So let's see if there's anything else. Hasn't been much. I mean, the David D. Hilster guy made a video just complaining about how dissidents don't do any work to promote dissidentry, you know, and yeah, the frank irony that most of them don't even pay attention to anybody else's theories, and they don't listen to anybody else, and they just couldn't care less. They just want to do their tinfoil hat thing, and they don't want to pretend they have to interact with anybody else. And that is sort of just so bogus. This expectation that somehow, if I'm not willing to listen to other people, then why should anybody listen to me, right? I mean, it's kind of obvious. So I think you really do have to pay attention to other people's arguments. I mean, you have to listen to them before you dismiss them. And you have to listen to enough of it before you dismiss it. You have to give it a fair shot, and not too many dissidents willing to fair shot anybody else's theories. They just want to call everybody a knuckle dragger or something and be done with it. You don't want to have to do any work. And obviously I have done that. I have played other people's videos and attempted to understand, attempted to provide an explanation for why I don't think it could happen that way. I've done that stuff. So, yeah, so there really hasn't been anything in the subscriptions worth watching. I mean, the Scientific League guy has just, left the building with this Jesus crap. It's just too bad. I did watch this Rational Science on how the battery works, but it's this rope theory, and it doesn't make any sense. It's a semi-good explanation of some of the mechanics of a battery in terms of talking about the acids, but it doesn't really talk about the ions or the exchange through the medium of the fluid and how it's creating one current, and the other current is just a byproduct of the current created in the medium. So, it's kind of obvious, and but yeah, it's this other stuff, it's all this rope crap that just really is useless. So, I mean, his arguments against conventional physics are watchable, but the rope videos really, once you've heard it and you've figured out how that can't, no way that works. Yeah, that's as far as it goes. So there really hasn't been much to comment on, but like I said, I don't need it because I got all these lectures to do. So that shall keep me busy for a lot of time. And like I said, it's really good for me just to listen to these things and see how, as I become more and more, as I understand more and more of it, I become more and more capable of noticing when they're just going right past something without explaining anything, without giving you a single bit of causal information. And again, the demonstrations can often be quite deceptive. So it's like Professor Lewin used grass seeds to illustrate the magnetic field. And I had to think about that for a while because I'm saying, why is he using grass seeds? Why doesn't he just use iron filings and something? And I'm saying, oh yes, this the electric field is, you have to create it in a different way, the magnetic effect, but it still has to be isolated. So So it's almost like you'd have to use like a ferrofluid or some other kind of mechanism, because the field effect would be to neutralize everything. Conductors aren't going to stay magnets in an electric field. They're just not. Where the grass seed does, because I guess the electric field keeps, because of the grass seed, it keeps, like a little battery, it keeps changing its ionic surface or something. And so it keeps switching its polarity, something like that. Or it keeps running around its surface or something. I don't know what exactly the thing is. But the seeds are in a medium. I mean, it's very complex. And so it's not a simple experiment in a way. It's not, it's, are you electrifying the medium and then that's affecting the grass seeds? Or are you, so it's just not as simple as it looks. It looks like a simple experiment, but it's not. Like the ferrocell looks simple. You're saying, how can this be lying to me? But it's lying to you. It's a deception. And you got to be so careful when people use an experiment, because it all depends on how they do the experiment. How close they move something to the charge will change whether it has a neutral in it. You could almost argue. Like if I move something close enough to something that's charged, like even the Van de Graaff, it might be harder to get a dipole, because of the fact that I don't have enough of a differential in the voltages, and the voltages are so high that the current will move too fast. I won't be able to separate them fast enough. So I might need a charge that's low enough where when I separate them, I can isolate the two charges. So there's a lot of conditions is all I'm saying. And they don't do the conditions. And so again, it goes back to the radar experiment, with the interference pattern. They give you this superficial, see, it's the interference pattern, but they don't give you the context of, well, there is this possibility that the two frequencies are out of phase and superimposed on each other. And if I take two frequencies that are the same and they're out of phase, I can't pick them up on a radio. Okay, that's just the way the rules work. Yeah. So it's tricky. So I showed you nothing because you can't see the YouTube page. So anyway, these are the other videos I am watching. The Shin-Kar guy from Yale. But yes, all mathematics mostly. But anyway, you really didn't see that, I don't think. So, all right. So let's see if there's any comments and shuffle off maybe. Yeah, nothing yet. So I'll give you a minute or so. Anybody's got anything to say, questions, comments, whatever. Insults, not really welcome. Arguments, welcome. Guess I could see how many people are here. Friday night, I guess that's a little of 13, so about the average. Not too impressive, but see, by the time the numbers get impressive, I probably won't bother doing this anymore because now I'd already won my battle. But I think I'm the kind of person who'd still want to argue with people about it just to defend it. I wouldn't want people taking cheap shots that don't get answered. So I think I'd always be available to answer critiques. Pretty sure. Oh, it's a list. I guess I could talk a little bit about the Deadpool. Yeah, that's going to be cool. I think David D. Hilstrom might be ready to ditch his expansion tectonics theory. Where do you see any evidence of that? He seems obsessed with it. He might go with your theory of gravity and say that the number or speed of force bits has changed since the dinosaurs existed. Again, the whole thing is silly. Dinosaurs are built like big, heavy fuckers. They're not built like tap dancers. It's just a silly argument. And there's so much stuff that goes into these questions about, what kind of atmosphere provides more opportunity. I mean, you could argue that the atmosphere was heavier in the era of the dinosaurs, and that it was probably a lot easier to fly, just because of that fact that it was like swimming. You could swim in the atmosphere. Grass seeds and iron filings, question mark. I don't know what that means. I'm just, my point is he used grass seeds to illustrate charge. So grass seeds move in in an electric field that like iron filings. Iron filings won't move in an electric field because there isn't enough magnetism coming out of the wire. But the grass seeds will align with the strength of the electric field, much the same way as iron filings. So I'm not sure of those connections. I'm not sure whether the grass seeds are just measuring the magnetic field. They might just be measuring the magnetic field. I'm not sure. I mean, clearly he's using a high voltage. I mean, a lot of amperage. So he's pumping a lot of amperage through two wires going through these grass seeds. So he's, I mean, a lot, like 1,000 watts, 2,000 watts worth of electricity at a low voltage going through these two wires to create electric fields around them. Now, obviously, if you do that, you're also going to create magnetic fields with that much current, even though you don't have much of a length of wire. So I'm just not sure which one it's demonstrating. I'm just saying that that's the point I'm making. It's like the ferrocell, right? I mean, the ferrocell creates a spectacular display, but the display isn't displaying the magnetic field. It's displaying a perversion of it based on geometry of how the little bits are reflecting the light and their position. So at different positions, they reflect all to one point, and that's why you see a curved line. But there is no curved line. It's completely an illusion. All the lines are straight and radial, and you're seeing a curved line only because the reflections are only happening off different lines at the right angle. And so it's a complete illusion. Very convincing illusion, but it's completely not the truth. It's not revealing the truth. It's creating a distortion. I'm just saying experiments are dangerous when they can do that. And that's something I'm starting to get a feel for, is that when he creates a dipole or something, he always knows exactly how close to get to the charges. He knows that if he goes too close, it's not going to work. If he's too far away, it's not going to work. He knows those rules. And he's not explaining that to us. He hasn't talked about expansion tech. You're wrong. He says it in every video. The last two videos he mentioned expansion tectonics, expansion tectonics. This is one of the reasons why we got to get rid of these dumbheads, because they don't believe the earth is expanding. He said this shit in every video. So yeah, you're just wrong. I'll bet you real money he'll make a video any day now, and he'll just talk about expansion tectonics and how this is the truth. What was I doing? Oh yeah, I was going to show the list of names for the Deadpool. A lot of names. So I should post them somewhere. I think I have them posted in the Deadpool video. I just probably have to update it if people want to add any. So you won't be able to see any of these names, so I'll have to make them bigger. Let's see, control and plus. We need a lot of pluses. All right, so we got lots of names, so it's pretty good. So Piero, Ken Wheeler, Hoffa Bay, Wallace Thornhill, Laura, Walter Lewin. So it's all people I have one way or another either contacted or who have referenced me in some point or have said I'm an asshole for trying this or something like that. So Miles Mathis, Modern Mystic, Crawford, Darwin's Hamster, Cowboy Guy, whoever the cowboy, I can't remember his real name. I just don't pay attention to names much. Mindless Marbles, David D. Hilster, Franklin Hugh, Jeff Yee, Harry, and Bill. They were the people in the room with the CPS guys. So Bill is the religious kook, the creationist, but Harry apparently is also sympathetic to Bill's theory, which must make Harry also a religious kook. Fractal Woman Scientific Lee warbles on a lot. Bill Gates' son, who I think he's hopeful. He seems reasonable, and I think if he actually watched one of my videos, he might get it. Physics Girl, 60 Symbols, Neil deGrasse Tyson, David Albert. Oh yeah, he was the guy I did the video on. They actually gave me a copyright thing on his video, which is just such bullshit, right? I'm playing clips of a physics video, and they give me a copyright notice. I mean, isn't that just so fucking bullshit? I mean, it's obviously fair use. I didn't just play his lecture. I obviously interrupted every 10 seconds. How the fuck could they call? How could they not know that's fair use? I shouldn't have to defend that. Just such bullshit. So I was thinking of having two prizes. A prize for getting the winners right, or the most winners right, the ones who turn, the ones who concede, the ones who have some integrity and concede. And then a prize for somebody who can get all the ones who will never concede, right? So all the assholes who just will be the last to accept reality. So it'd be interesting, to do it both ways. Pick the most people who will convert and in the right order, closest to the right order, and the inverse. Pick the ones who'll be last to accept it and get obviously can't get those in the right order. Yeah, obviously. But pick the 10. We'll say the 10 people. You put 10 on the list, and if you can make a list that doesn't have any wrong answers on it, then you'll probably win. And if there's a tie, you'll have to share the money, that kind of thing. Yeah, well, it's fine to say Ken Wheeler does metaphysics. He's obviously disguising it as physics. So, regardless, I mean, I think obviously he's doing religion. He's not. I don't think there is metaphysics. I don't know why people use this word, because to me it's an obnoxious concept. This meta thing. I don't understand. It either is physics or it's not physics. I don't understand how you have something called a metaphysics. Yes, that's brilliant. I farted in my diaper and some poo came out. Wow. It's just really interesting. Lots of people have little fetishes about pooing and being in diapers. So there's probably a group somewhere online, actually, a Facebook group for diaper pooers. And, you could probably hang out with them, But yes, you're sort of an example of why humans should be eradicated, without any mercy, really. The fact that we don't have you in a little padded room is one of the reasons why we fail as a civilization. I'm just sort of amazed that people want to keep pointing out to me how I'm absolutely correct that humans aren't worth saving. It's just so funny. Well, I have to get that guy. I can't let him be right about anything. And they just provide the evidence of my argument. They just say, here, I'm going to show up with the evidence that we are assholes, that we're imbeciles. We can't make an argument. We got no grounds to stand on. We're just bigots and idiots. And we don't know nothing about nothing, and we can't figure out how to make a rational argument. So all we can do is talk about our pooey diapers. Yeah, okay, you just made my argument for me. Shit. Thank you. So, geez, just amazing planet. Amazing how neurology can go so wrong. How many of these people have actually made an honest effort to understand your model in recent times? I'm wondering. Well, exactly the point. I mean, obviously, it's physics. I mean, obviously, you have to put a little bit of time in to kind of get it. So I don't know how much. I mean, I'm just saying the overview videos seem to me pretty compelling. If somebody can watch those and just say that can't possibly be right, then I think they're an idiot, because it can quite possibly be right. So that should inspire in them some willingness to say, I got to find a loophole. I got to find a reason why that can't be right, because that looks too good. And they don't seem willing to put any effort in to do that in any kind of reasonably polite way, anyway. So, like I said, you got to generate interest some way, get people to pay attention. But I'm just saying, I have so many pieces now. I'm just saying that anybody who has seen these recent videos would just have to, I think logically, anybody who's intellectually honest has to concede this is a well-constructed, well-developed contender. All right, maybe it's not going to win, but it looks like a winner. It's wearing the right shorts and it's got the right shoes and Nike thingy, and it's got muscles and stuff. I mean, it looks like it can win. Well, it seems that way. I'm just saying, I thought people were more intellectual than it appears they are. That the reason why all this silly answers, physics just keeps coming up with sillier and sillier shit, right? I mean, they're talking now like they photographed an electron. They're actually saying, "Oh, look, here's a video of an electron." No, not even close. Here's a picture of 5 atoms and an electron. Not even. No. And then it's like this dark matter thing, all this spooky action experiments, completely convoluted, bizarre stuff, and everybody just follows along like, yeah, that happened, sure, yeah, tunneling microscopes and tunnel vision, yeah, sure. So they do seem to just say, oh yeah, give me the wackier the better. Tell me something wacky and I'll believe it. Yeah, well, and one of the logical tests is it unifies. I mean, it's a huge plus for my version of reality is that it actually does unify the force. It does what Einstein spent his whole life looking for. And it does it really simple. It does it in Feynman's way. Feynman speculated that the truth could be it's all just a big checkerboard, and we're getting lost in the fucking size of the thing. We're little things moving around this huge thing, but it's dead stupid. It's just that we can't see the simplicity because we're so caught up in the complexity. Yeah, good example. Holographic bullshit. Oh, there's a there's a little recording of everything that happened in the universe in the singularity hole thingy or whatever it is in the whatever you call the event horizon has all of your embarrassing moments written right in it, and someday everybody can watch them. I mean, it's just such a pile of horseshit. Well, again, I don't need special relativity. I don't need any fucking nonsense about how there's a time dimension that's warped. It doesn't make any sense. Why would my theory be agreeable to bending photons, bending a straight line? Why would it say, let's bend straight lines for no good reason? Yeah, there's nothing in my theory says that makes any sense. I mean, all of special relativity is based on a stupid, number one, the bending photons is kind of irrelevant. There's no practical purpose to it anyway, so it's stupid. And the rest of the relativity theory, the only evidence of it is this stupid time dilation. As I've explained, the time dilation is so easy to understand as just being the exhaustion of the matter. The matter moving is tired matter. It's already doing something and you're forcing it to move. So of course it can't do what it was doing at the same speed. It can't clock at the same speed as it was clocking because you're forcing it to do something else. You're saying do clocking and move. Well, of course it can't clock at the same time. It's multitasking. It's got to fucking slow down. You can't clock at the same speed if you're telling it to walk somewhere. Shit. Go upstairs and then go downstairs at the same time. Of course it has a problem doing that. They are actually smirking and laughing under their breath through the entire presentation I've seen. Well, I don't know about that. They seem pretty convinced. The lecturers I've seen talking about all this black hole bullshit and all they look like they're jerking off to it hard. Relativity. Do you reject it? Of course, I reject it completely. There's no fucking time dimension, for fuck's sake. There's no time is a function. There would be no time if photons moved instantaneously. So the fact that they're a little slower than instantaneously means there's a universe. Period. There's no other reason. Time is nothing. Time is just a byproduct of stuff moving slower than instantaneous. You can't help but make time when you're something other than instantaneously doing something. Distance takes time, period. That's time. Time is a done subject now. The past is gone. The future ain't here yet. There's no traveling either place. It's all horse shit. It doesn't matter whether it's general relativity or special relativity. I mean, obviously, it's just him restating the original theory with more specifics. So he says, look, here's a special circumstance of acceleration. And then he basically says, well, fuck the special circumstances. Let's just talk about the fact that everything is the same. And it's not the same. All acceleration isn't the same. Our capacity to see the difference is the same. We can't see it, but there are differences. That's exactly what I'm pointing out. I mean, obviously the force is different when the electron is reflecting more of one kind than another kind. But Einstein doesn't even understand that there's forces. He just has this idiotic bent space crap that duplicates the inverse square law, which I'm explaining why the inverse square law is a radial force law. It's not a bent space law. You say it works with the math, but it doesn't. Because it does do the idiotic things where it makes it possible to have two frames passing each other in such a way as you reverse events. You watch somebody die before you watch them getting born. That's obviously not math that works. One thing I'm thinking about is the background of force bits. Well, I had a thought on the background problem because this, I've said it before that, it's kind of ludicrous that the photons leaving the universe are coming back, but they really are. Because if you really think in terms of infinities, all right, forever, the fact is you have to assume they're flying into gravity just like we're existing in gravity, and that they are going to encounter this fact that the gravity that's hitting them from the place they're going is stronger than the gravity from the place they left, because the place they left has a bunch of matter, right? And it's absorbing energy in their direction. The matter could be thought of as the whole universe could be thought of a giant planet. And as the photon's leaving the giant planet, it's slowly going to lose its acceleration. And this might be why the stupid satellites, the Voyager and the other one are slowing down a little. Well, they're probably doing it because, or speeding up. One's speeding up, one slows down. They're probably doing it because the local universe is really hard for us to calculate. We have a real hard time. Without going out there with a compass needle, we can't tell what's going on exactly in terms of how much mass exactly is this way and how much mass is exactly that way in the galaxy. The galaxy has disproportional mass in it. So we can't assume that the gravity, quote unquote, is going to be the same in all directions, because clearly we're going to be heading for more mass in one direction than in the other direction as a fact. So of course it could accelerate because there could be more mass that way. It seems like an obvious answer, but the thing is the photons theoretically, because of the gravitational difference on them, would slow down. But again, my argument is that photons are force, and force can't interact with force, so they couldn't slow down. So forget what I just said. Yeah, it still makes no sense. The force can never be changed, except it can't be changed. The force doesn't stop. It has to hit a brick wall. So unless there's a membrane around the universe reflecting the stuff back, it goes forever. But maybe there's just more clutter. The universe is full of clutter, and the photon is inevitably going to hit something and come back because there's still clutter out there. So eventually it's going to hit something and come back in. So nothing can ever escape just merely because there's so much crap in the universe. Something like that. I don't know. It is a problem that I think you need to make the universe have a membrane. It works better if you have one, if it's a bubble and the stuff is reflecting back. So light photons go out, bounce off the end of the universe, and come back as gravity. Then you're explaining where it's coming from. And you keep equilibrium. You conserve the energy. Well, I don't know. If there's more mass, there's more occupied force, and thus the force behind you increases. I think that's said backwards. If you're leaving a mass, if you're heading towards it, yes, then you'll go faster. But it's not because gravity got weaker, it's because the stuff in front of you got weaker. I think you said that backwards. Yeah, well, there's lots of spooky stuff to life, lots of little coincidences. When I was 5, 6 years old, 7 years old, probably up to like 8 years old, every night when I went to sleep and the lights went out, my room would fill with little dots of light. And they were really like little pieces of styrofoam or something. And they moved around like little pixels in a screen of little color, blue and red and yellow, the primary colors mostly. And they swirled in all kinds of patterns. And it was really interesting. I used to have dreams where I flew a lot back then. Like almost every night I would dream I was flying. Flying like not Superman, but kind of floating, and I'd go faster and I'd go slower, and I could kind of, feel the ground and be able to manipulate my, couldn't land worth shit though. So it was always a mess landing. But anyway, the little dots were, it's just so interesting. That I was doing physics in a sense, when I was 5 years old. See, we don't really have a good explanation for the cosmic background radiation. Because clearly by their dopey expansion theory, especially the part where it expands 10 million times all at once, that just doesn't make any sense that the cosmic background radiation would go with the matter, magically. Somehow the photons would be moved, dimensionally in space, this preposterous amount. It just doesn't make any sense. They could go the speed of light in one direction and they could go 10 times the speed of light in another direction at the same time. I mean, it just doesn't make any sense. So they need a better explanation for what the cosmic background radiation is. And I would argue it's just randomized gravity. Every now and then, gravity makes a photon by accident. Yeah. And it seems kind of logical to think that it would make it's kind of funny. The microwaves is sort of in the middle of the scale, right? Microwaves kind of in the middle of the scale, towards the middle anyway. I don't know if they're, I have to look at it to make sure. Obviously, the top end of the scale is infinite and the bottom end of the scale is sort of infinite. So who knows where the middle of the scale is, right? Lots of good explanations, but one wrong. Well, it seems like you're kind of wasting my time pointing that out without pointing out what you think is wrong. So I just don't see the point in it. You're warning me that you're going to make a comment that's relevant. I'm warning you, I'm going to make a relevant comment any minute now. Okay, make it, please. Please enlighten me on the wrong. The one wrong. I'm sure I've gotten more than one detail wrong here, but anyway, go ahead. Makes sense. You'd think the gravity would be bound to have some random photons pairs. Yes, every now and then, especially if it's bouncing off of something, right? Especially if it is a reflection, off the end of the universe. You could have two coherent photons that end up hitting each other at the same location and then reflecting, some bizarre little thing could happen where, oops, now we've just created some gravity and a little bit of microwave energy. All right, so now he's saying there's something wrong with this. Look, anything I say about cosmology, all right, the Big Bang or expansion, or that's as draft as it gets, because frankly, we just got shit for evidence. So I don't, say I'm wrong about something. It seems idiotic because, unless you're going to point to an experiment or something to prove something or whatever, and I'll prove how that experiment doesn't really prove anything. But nobody can know these answers. There's just too little evidence. So he says Big Bang expansion of background radiation is wrong. Well, I'm sorry. Their explanation, I've heard it come out of their mouths, okay? They say the Big Bang happened this way. Boing, okay? So there's this boing part in the middle. And the point is that everything's moving apart from each other. So everything's separating, right? Moving away. So if you do the surface of the balloon part, it's okay with me. So the surface of the balloon, they moved a little bit away, and then the balloon blew up, and then they went a little bit away again. All right. So the point is the background radiation is moving the speed of light. It's already going the speed of light. So it's one thing to say matter can boing, but it's another thing to say that you can take something going the speed of light and boing it, right? To me, that doesn't seem very, where it just goes and then continues to go the speed of light from this new location. That to me is just incoherent. That's all I'm saying. But that's what they say happened. The cosmic background radiation is trapped with the matter that it was near, quote unquote. And so as the expansion happened, it expanded with it. That's how I understand their theory. Tell me I'm wrong, fine. I don't know what to say to you except that's what I've heard them say. So I guess he's saying they're wrong. I don't know. See, this is why these small sentences really aren't very constructive. I mean, I don't want long paragraphs, but I just mean when you say we have no context. So maybe he's saying lots of good explanations. So they have lots of good explanations of what's happening in the cosmos. I'd say they have shitty ones. I don't think they even get galaxies right. Galaxies are expanding, not contracting. But one wrong. So maybe he's talking about them. I mean, no offense, John, but I mean, you don't make comments that are we don't talk the same kind of language. I mean, maybe you're just doing nerd talk or something, or bicycle guy talk, and I just don't get it. But I'm just saying, I just don't know sometimes what the fuck you're talking about. Well, look, all we know is that there's radiation coming from the whole universe in a fairly random amount. I mean, there's patches, but it's blotches, but it's pretty randomly coming at us like gravity would be if gravity was such a force as I think it is. Yeah. Lots of good explanations of background radiation. Well, whatever. I don't know what you're doing still. There's no context to these, these sentences. They're just totally not constructive. What do you mean by lots of good explanations? What do you mean there's lots of the quacky ducky theory, where the duck is quacking and that bounces off the membrane and it, comes back as cosmic rays or something? I mean, what do we mean by good explanations? The black holes, hit each other, and that makes cosmic background radiation. I mean, what theory are you talking about that's good? I think they all suck. That's my opinion. They're all weakly evidenced and sound sissy crazy to me. There's a warm puppy at the center of the universe, and its love produced the radiation. Love, love. Of course it's warm, because it's love, love. Yeah, the aliens are talking to us. There's probably people who think that's what it is. Yes, it's a bunch of alien hieroglyphics, full of all kinds of detailed plans on how to make the great big teeter totter that'll send you through the wormhole. Maybe it's a distress signal. Yes. There's a bunch of aliens trapped in a lifeboat. They need our help, and we've been goofing off all this time, not hearing their desperate message for help. Yeah, well, see, people do say some funny things, right? Because the rational science guy, right, Bill Gates. So he was ragging on black holes in one of his videos, and he started off with something painted black, and it was just kind of funny because he was saying, "Look, I can see it," and I was like, "No, you're not getting it. You have to put it on a black background. You can't put it against your white shirt and say, 'Look, I can see the black hole.' No, 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 no. You have to put it against the black background." So I was just like, oh, you're missing the point here. It can be black and you won't see it. If it's really black, you really won't see it. The space isn't white. Uh, well, you could argue that there's that much scatter, but I guess you'd have to prove it somewhere, right? I mean, that's a lot of scatter you're saying. So the argument could be made that then why isn't that scatter creating all kinds of distortions in our view of the universe? So we should be saying if see, I say the hydrogen in space is causing the redshift because the hydrogen atoms it hits see more hydrogen atoms will be going towards the thing moving, right? The hydrogen atoms moving the same way the photon is going can't catch up, but the ones moving the opposite direction will be imposing their force. So if a photon's traveling through a field of hydrogen atoms moving in all directions, it's going to hit more going forward than any other direction. And the forward ones, right, are redshifting ones from the direction the photon's going. So when the photon hits the hydrogen atom, it's transparent, it goes through it okay, but it gets redshifted because now it's being emitted by a hydrogen atom moving the wrong way, so it's redshifted. So each time the photon hits a hydrogen atom, it gets a little tiny bit of redshift. So the further away something is, the more redshifted it is. Oh, that answer is so good. Now, how could a logical person say that's not a great answer? That's a great answer. 2.4K. It's just, again, I'll just make the argument though. I would have to have a demonstration of the fact that that much scatter exists because there's no, I haven't seen any evidence of that much scatter in terms of space being that cluttered enough to create that much radiation. So you say it's just 2.4 Kelvin or something or whatever the hell you're saying, but clearly it's enough where you can tune it in on a radio, you know? I mean, it's not an insignificant amount of radiation and it's on lots of bands. So you have to add up each band that it's being created in. All the photons we're not seeing right now. You know, there's visible light in the background radiation. We just don't see it because it's very short rays. We don't see short rays of light. We need to be hit by multiple bits of energy to see the photon. We can only see long photons, long rays. We can't see short rays. Yeah, it's something I have to write down. I haven't written down my redshift theory, but it just makes so much sense to me. I mean, it really nails it, I think. Gotta write that down. Redshift, gotta get to that. Ugh, so many things to do. So much work for one man. COBE. Oh dear, that's probably some dopey satellite. The kooky obligatory bullshit experiment. Oh yes, Cosmic Background Explorer. Oh, well, you're missing the O though. Oh, it's exploder. Yeah. Let's make a Kobe bomb. Yeah, I mean, there's it does this get tricky just because just because we can't see very far. 13 billion years we can see, but just the whole question of there's just as many photons going the opposite way, so to speak, than the ones that went our way. There's for every left, there's a right. So obviously all these photons from the universe are coming towards us, but there's just as many photons going the other way. You're just trying to figure out, well, where the hell are they all going? But don't get me wrong, I'm totally not. I'm not opposed to the idea of scatter being the cause of the background radiation. I'm just not sure that you know. I'm not sure that I've seen anything other than the fact that let's blame it on something. Sounds cool. Yeah, I'd like to blame it on something. I think the simple truth is the universe in its fundamental state, its most elemental state, was just force. Little stuff buzzing around at the speed of light, and that the matter condensed out of that, and that it is going through this process where the energy gets stuck together, and that pressurizes. And as it pressurizes, all the force bits are starting to get stuck inside the matter bits. So the energy equation becomes more inside than outside. So the gravity diminishes over time. It's weaker and weaker. And there'll be a point where a kind of broken equilibrium. It just be a point where there won't be enough gravity to maintain the pressure and everything starts to expand. And I would argue that that's sort of being evidenced in the fact that galaxies are falling apart. So in the old universe, the galaxies were held together because there was enough gravity. But as the galaxies started absorbing everything, they absorbed it all. The gravity got weaker, and now the galaxies are falling apart, and that's releasing energy, which is making the gravity stronger again. So there'd be a point where the galaxies stop expanding and started contracting again. I think it's something like that. But again, it's not completely out of my ass, but it's only based on the fact that you have to have some accounting for the conservation of the energy. So that's my effort to account for the conservation. Yeah, well, Ken's theory is the hard light is protons. He thinks there's only. Oh yeah, and what does he call the photons before that? So they're not waves, but he calls they're perturbations or whatever. They're non-magnituded perturbations, and then they perturbate so fast at so high a frequency that they turn into protons, which seems like a hell of a leap, right? I mean, photon to a proton. That seems like a hell of a leap. I think you need a few steps in between, right? I think you need a lot of light to make a proton. This seems like it can't be made out of one little photon. Yeah, every 3 or 4 years, Ken does say a couple of words that he did say compressions and refractions. So instead of saying compressions and expansions, but yes, that's a good concept, right? The whole universe is just compressions and expansions, you know, so that fits with my theory. But he says so many things that are just so stupid that you can't give him any credit because most of the shit he says is just crap. All this hyperboloid and troiloidal crap. It's just, oh, I mean, I can't believe that people can't just say themselves, I do understand that you can't create a tornado in space. You have to have an atmosphere and you have to have lots of stuff to make one. Can't just make tornadoes out of nothing. Where's all that energy come from? I mean, fuck, the tornadoes are in magnets. They're full of tornadoes. Come on. Well, you can just sort of logically understand that if you were able to destroy a proton, you can sort of surmise that it would release a ton of photons. So it can't possibly be made out of one photon going too fast, you know, having too high a frequency, right? It's just logical. It's got to be made out of bazillions of photons because that's what it will release if you could blow one up. Well, again, saying metaphysically lacking doesn't make any sense. There is no metaphysics. Nobody should be doing anything called metaphysics. Metaphysics is retarded as a concept. It's just saying retarded physics, non-physical physics. It's retarded, stupid. But you should say metaphysically challenged, not metaphysically lacking. It would sound funnier as a joke. But he's actually logically challenged, you know, rationality challenged, certainly fact challenged, evidence challenged, full of shit challenged. Yes, the old dielectric. The dielectric. Dielectricity. I love that term, right? Dielectricity. As opposed to electricity. Yeah. I'd love to see somebody show me a bottle of dielectricity. Yeah, it's just like electricity, except, well, it's just like electricity. Yeah. It's just a funner word. Pervertivations. Yes, very good. The ferrocell is the dielectric perverterator. It's a dielectric perverterator. Oh, yeah, capacitor, the capacitor stuff. Oh, he makes me crazy. The smaller the space, the more capacitance. No. Not correct answer. Obviously, there's more. It's by the inverse square law. The closer you put the charges, obviously, the more force you got. You know, you're maximizing how much force transfer you have between the two plates. But you need a ton of capacitor to have any capacity. You have to fricking roll up 4 miles of foil into the capacitor to hold any electricity. So obviously it takes a lot of space to hold electricity. You can't put electricity in a small space. If we could, then we would have electricity in small spaces, and we really don't. You have to use these freaky batteries and shit. Well, it's just so obviously, it's kind of just silly to say, just because we know big capacitors, big capacitance, small capacitor, little capacitance. I mean, that's just kind of obvious, for fuck's sake. I see where they're doing the high voltage DC for that they're making some new electric lines now in certain towns or states, and they're using high voltage DC. They're going back to old Edison's thing, and it's kind of interesting though because they have to use these, gigantic capacitors to be able to four-way bridge the frickin' DC current to turn it into AC current so they can transform it and so they can put it back. I mean, they have to go through AC to get any kind of ability to change the voltage, to make voltage changes. But it really is interesting. I always like DC. It does make so much more sense. But it would be interesting. I mean, I don't recall if I've ever been electrocuted by like 400 or 500 volts of DC, whether how much you feel. Because you certainly understand how the AC is a bitch going through you because that's jerking you around, But the DC would be pressurizing the fuck out of your atoms, so it's jerking you around, but at least it's not making them small, big, small, big, small, big. It's not doing that thing. I mean, I think the frequency of AC is what makes it so dangerous. It's the fact that it's vibrating you. The vibrations are what's breaking everything, burning you up. Not working. No battery. How could that be? Batteries wear out. Damn. Who thought of that bad idea? Yeah, just put in one of these new ones there and then pop that in. I'll be ready to go again. I should be using the little one. Wow, we have some new gigantic lines being put in here right across my land. Yeah. Well, like I said, if it's DC, at least it won't be radiating as much energy into you, as I understand it anyway. Yeah, a little bit ironic. Coincidentally so. But it seems quite inevitable that almost every subject I'll have to change a battery, right? Just because I just keep burning nicotine. More. I really have to get a nicotine pump. Just stick a couple of syringes in my head, into my brain. How one of those caps you can wear with a beer, and I'll just have it pumping in. And such. Yeah, thank you for the participation. Very good. Some good subjects. Reminded me to get to my Redshift writing and some other bullshit I have to get to. See, there's just so many subjects. There's so much covered by physics. And to get yourself up to speed on all of it. Whew, it's a lot to it. But it's so simple. Really should be easy. See, it's going to be easy for the next guy because he won't have to go through all the struggles of all the mistakes and all the, oh, no, I did it the wrong way. I should have thought of that. I should have thought. He won't have to do any of that. So it'll be really easy for people 10 years from now. But it's kind of rough on the inventor. Yeah, you would think the whole grid thing would be shrinking, just because if they did this solar thing the right way, they'd have, see, they really should have stuck with the Edison plan, where you distribute your power stations locally I think that would have been so much better an idea. I mean, obviously, you can't take advantage of the, you have the Niagara Falls. You want to take advantage of that. So you obviously have to distribute that power through lines. But the idea of transferring power from Iowa to, Tacoma or something is really quite stupid. Yes, well, everybody uses three-phase AC. So even though they're using DC to transmit, it'll still be three-phase AC in your house. I mean, we can't fix that everybody's appliances are AC appliances. So, they're not going to start pumping DC into your house tomorrow. But frankly, I'm trying to do it here. I got some solar panels and I'm trying to run, I'm trying to create a 12 volt system inside the house. So I always have some 12 volts somewhere I can just plug into my 12 volts. So eventually I want to have that, but it's the price of batteries. Unfortunately, I have to find a way to store energy. So I've been thinking about storage systems, from flywheels to all the different ways you could store energy. So I haven't thought of any great one yet, but I'm working on it. Maybe I'll invent a battery while I'm at, this project. Will end up making a new battery, because I do spend some time contemplating. It shouldn't be that hard to store pressure. That's all you want to do is store this freaking pressure. Yeah, well, if you have time to try to do the simulation, like I say, I worked on it in past videos. You can see that. I mean, I still have that thing up. I should be able to show you that image of as far as I went, and which wasn't very far. And it looks pretty cool, but I just haven't. I just don't have the fucking time to do it all the way, the right way. What do I need here? I want to jump to YouTube up. Okay, so there's YouTube and somewhere around here. No, that's not it. It might be this thing. There it is. Magnet. So it's a way of simulating that the mixed black and red force comes into the magnet and it comes out mostly black and mostly red. So like I said, I haven't finished it, where the force is coming in mixed and it comes out segregated. So I have to work on that part, but it's a very good little simulator. Yeah, it just doesn't seem likely that I'm going to come up with a new battery, because it seems like people have been working on it forever. And the basic principle is simple, but whether they know it's pressure of atoms, or they think it's electrons, or they think whatever they think batteries are storing, the idea that it's storing shit is all understood. So it's not like I have some huge advantage where, wow, I know exactly how it works, because I don't. Knowing how it works doesn't give me any huge advantage in saying, oh yeah, I can make trees into batteries. No, maybe not. But capturing lightning and stuff, that would be so cool if we could capture the energy in a lightning bolt. It's a huge amount of energy. Yeah, it's a great illustration. I just think it's brilliant. It's just all in HTML. I can run the whole thing in a browser window. It's going to be so cool when it ever gets done. When it ever. There's so many things to learn. I would love to just spend my time programming in this canvas function in HTML, because there's so many things you can do with it. But I'm just not good enough. I mean, it's a lot of math, and a lot of math that I'm not good at. But really, it's cool. I mean, even does, in a sense, the inverse square law. I mean, just sort of, you get the idea: weaker, 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 weaker. Very cool. Yeah, well, I wouldn't call it a rabbit hole. Coding is not exactly, there's no incoherent mush in coding. I mean, it's the only thing that's almost upside down or silly is the languages and the silly words they use or the silly rules about how you phrase, your argument. That kind of stuff pisses me off. One fucking misplaced colon and the whole thing fails. I have to see what it looks like. Oh, okay, it's a little bit too low. Well, it'd look a lot better if you saw what I'm seeing. Yeah, because I have part of the screen cut off. So the black side goes all the way over, and can't really show you how it really looks because I can't center it on the. I can't fix it because if I fix it, I'll break the video screen. So I don't want to do that. I have to run it in the other browser maybe. So if you got this, so the real effect is just shift the whole thing over so the black and the red are even sized and it shoots out evenly and it's much more impressive. So sorry that it's broken. And the frame rate isn't any good either, so that screws it up. Looks a lot better at the appropriate frame rate. No, get rid of that. Okay. Yeah, I really like the original, like assembler was so simple because everything was just go to, if then, it was all simple. No bullshit. But I know it would be everybody else would hate it if functions had names like 302, and that was the function's name. So I know people want functions that have names they understand. But yeah, I just part of me likes it to be very austere. Yeah, not wordy. I don't like wordy code. I hate that you have a whole big word, like you have to type the word correctly and then, so you automatically have to code in a spell checker and a this and a that. And it's just kind of irritating because why should I have to type 42 characters to basically just say go to? Yeah. Yeah. Well, I'm a terrible typist. So it just, I have to do cut and paste or I'm fucked. So I do an awful lot of cut and pasting. Yeah, well, I just mean that there is software that really isn't that bad. I mean, I even in just doing JavaScript, there's some old programs from like 15 years ago that are pretty good at picking up your errors, so I can't complain. Um, but I just don't find it, I don't like using one of those things just because they tend to also um, force you to use their style of code. You know what I mean? So it's like you have to rewrite their bad code. So you end up having to reprogram the program to write it your way, not their way. Yeah, yeah, exactly. This function does stuff, and then it goes to another function that does some more stuff, and then it does this really cool thing later. Function. Great. Thank you. I love that. I love a 4-paragraph function. Thank you. Now, I tried to learn C++ years back, and I hated the visual stuff. I just can't stand that way of coding. I hate it. I just hate it. Ugh. Object oriented. It's just very unintuitive to me. So the only programs I ever I'm just moderately useful at is JavaScript and Perl. It's the only ones I have to use for the internet. So they're the only ones I know with any kind of, I can get by. I can do sneaky things. Well, I've done a lot of interesting things. I mean, I can pop my little window on here, and it's like it won't show up on. Yeah, so no point in me popping it on, because you won't be able to see it. All right, so forget that. But I made these little toolboxes that you can just pop on with bookmarklets into the code, and it completely recode the page, and does lots of good stuff. But you have to have a mechanism to utilize it where people are participating and stuff, and I could just never get enough real people to give a shit. But it was a pretty good invention. I mean, it automatically does live chat. You can just live chat with somebody who has the tool. We could just live chat anytime, and it's pretty quick, back and forth. Yeah, I just found it terrible to try to code in Windows. You really had to learn. It was like learning a language, because you really had to learn what they called every menu and every sub menu and it was like, I don't want to learn all this crap. I don't want to know. I just want to be able to create one. I just give me a template that has everything in it, and just let me rewrite it. Just give me the template of a window, and then let me put all the functions I want in, and not ignore everything else. Just make everything else a not. Something like that. I don't know. But yeah, I couldn't get the hang of it. I couldn't get a feel for it at all. I liked what did you call it? The original Basic. Yeah, Basic was sort of a fun language, simple. Yeah, it's just like I kept making mistakes. I just kept putting things in the wrong menu, and I keep putting it, and I was just like all the time I was wasting trying to figure out, oh, that's the place. Oh, I can't get the IP address unless I do this first, and it was a nightmare. Yeah, Basic was almost like a go-to language. It really was kind of simple, but it was powerful in that way. It just, it gave you functions. It just allowed you to do things that were, yeah, you want to access this port? Sure. Here's the port number. No big deal. I mean, the problem is once you got to a port, it didn't give you any interpreters, so you could actually tell what the stream was saying. But you could get to the stream. You could get to the information. You just couldn't decipher it. You know. Yeah, well, the memory problem is basically the Microsoft infrastructure. So I don't even know why they, it's like Linux didn't do that great a job of fixing any of these memory problems either. It's kind of a, it's got some glitchy shit, and it's better, but I mean, it's still. I don't see why there's such an issue. You should be able to figure out what stuff is important data and which is bullshit data, and figure out how not to waste, and or to let programs just use up everything. I mean, it should be rules like you can't use all the memory on the computer. I mean, you'd think they would have blocks against that. It's because, like, I had this program that worked really well at accessing both my webcams, but then it got broken on the update, and the program would actually write temp files that would consume every bit of hard drive space. So it ate every single bit of the hard drive. And you're just saying, why isn't there a thing in the operating system that says you can't do that, you fuckhead? Yeah, well, that was a big difference, though. I could understand why the 32 to 64-bit thing created all kinds of compatibility problems because, yeah, I mean, everything's, that's a huge change. I'd almost argue that that's when they should have decided to do a restart, redo the operating system, just forget about backward compatibility and just say we're starting over. Or create a simulator, let people do backward compatible, but they do it in a simulation, a virtual machine. They should just create virtual machines for compatibility and then just redid the whole thing for 64. Because that would have been so much better than what they did, which was try to be backward compatible with some stuff, but not everything. Because it's like, Windows 10 broke like 4 programs I really liked. It was like, yeah, Windows isn't of much value anymore because 4 programs I really like don't work on it. You know, so it's like, why bother with the half compromise when the half compromise, compromises too much? But Windows 10 should have automatically run a simulation, a virtual machine every time you wanted to load a 32-bit system. It should have just said, okay, we're going to load. It's going to kill a little bit of your memory, but we're going to load a simulation, and it'll run slower, but it'll run. And that's what they should have done. Yeah, well, the internet really is quite evil, and everybody's, yeah. It's just very disappointing that computers, yes, it's like Microsoft and Google. These are the wrong companies to have deciding infrastructure. They shouldn't be writing our infrastructure. Yeah, an emulator is what I'm trying to say. I'm just not saying it. I haven't tried the Linux emulator yet. I have to get around to doing that, whatever it's called. Yeah, just too much to do. I have to learn how to use GIMP. You so much to do. But yeah, the last almost 2 years now, I've been running Linux. I really haven't. There's been a few times where I thought about, oh yeah, I'll put XP back on. I have an XP drive, so I can just run XP anytime I need to, and run my old software. But it's like, yeah, that'll take 3 minutes. The hell with that. It's like it's just not important enough. I can do most of the stuff I need to do with the Linux, so I just don't bother. Yeah, I know. I didn't think I'd be this easy to slide into it, but Mint it's so like Windows, it's like Windows. It feels like Windows. It's got a windowness to it. So it's just like, yeah, this is easy. And it really isn't. I mean, just getting it, getting your drivers right and getting certain things right. You have to do some crap in the terminal and you have to fix a few things, but once you get it set up, it it just doesn't. I had a problem where it was kind of crashing once a week, but I mean, neither one of these systems ever crashes on me. I mean, even this. I mean, I'm running two video cameras. I mean, two webcams, plus doing this whole windowing thing, streaming it in OPS, OSB, or whatever it is, and it's doing fine. And I've got like 40 tabs open in Firefox, plus Chrome open doing this because I can't do the streaming in Firefox. And yeah, it's handling it. And this is not a good computer. I mean, this is a $200 computer. Yes, I probably should have a lot of draft, a lot of draft channels. Uh, Draft toenail polishing, draft, eyeball reorientationing. Yeah, and the great thing is this version of Mint will work on all my computers. The laptop, this, so I can move it to I can move it anywhere I want to any device, and there's none of this crap from Windows like, oh, you've changed something. We can't allow you to change anything. It works just like you had it on the other computer. I mean, it's you just don't have any hassles in moving it. And once you got it going too, it loads fast. I mean, under a minute. You're going to do it now, right? I'll do the 45-minute simulation of everything you've talked about. Yes. Okay. Hopefully it'll work. But yes, thank you. I mean, I appreciate anybody trying to make, you know, contributions. It's excellent. Fantastic. Oh, anything cuts my workload is appreciated. Guess we don't need the Deadpool list. It's kind of uninteresting. All right, so probably should get going. Yeah, I haven't had a talk room for a while, so I guess I felt like talking because I so obviously stayed in here a while. So anyway, it helps sometimes to think when interaction helps, and it's just but it has to be somewhat constructive, somewhat polite, you know, but it is really helpful in terms of the thinking process. It keeps you on your toes, kind of thing, and forces you to fix what's broken. So I like doing it. Anyway, so thank you for your participation. Some good subjects. Uh, yeah, good on you people. Yeah, yeah, it sort of is. You are kind of using them as a whiteboard, but yes, it is. Error code, right? Error code makes good evolution. So you need some errors to make things work. Yeah, we don't really have to do thousands, but I think a few hundred will be illusion enough. So if you can get a few hundred bits to move around at this, simulating the speed of light, bouncing off some electrons and protons, and then you'll be way ahead. So anyway, and the key point is how they reflect. It's the way they reflect. The key to the whole thing is reflections. It's what things reflect. It's what the atom reflects. It's what the electron reflects. It's what the proton reflects. It makes all the difference. I have to keep that word in mind. See, these are key things. Pressure is a key thing. Reflection is a key word here. It's about the reflections, because that creates the traps. The reflections are the first step to making a trap. All right. So again, thank you, and pleasant whatevering until the next time and such. And I have to have whatever window I have to have open to get out of here. All right. So till the next time and such.